Welcome back. Today we are doing a really fascinating, almost surgical deep dive into the architecture of automated expression. We're looking at source material from Architettura Segreta della Prosodia in pure data.
Yeah, and this is for you if you've ever wondered how music and linguistics and even computer engineering can all merge.
To do what, exactly?
To mimic one of the most fundamental human things we do, the rhythm and the melody of just talking spontaneously.
So our mission today is to really get under the hood of this one unique software object. It's built in pure data, and it's called Prosodia. And the whole point was to generate Italian speech that feels expressive, nuanced, and, this is the key, is always non-repeating.
It's like a machine that speaks, but it never, ever reads from a script.
But we need to be really clear up front about what speaks means here.
Absolutely. We have to be crystal clear. This is not about synthesizing the actual sounds, the vowels and consonants.
The phones.
Exactly. You're not going to hear an actual word. The entire focus is on the architecture of the prosody.
The rhythm, the accent, the pitch.
The melody of it all.
Yeah.
The core problem they were trying to solve was how to give a machine the ability to breathe. To use the natural melodic shape of a language.
To make it sound human, even if the sound itself is totally abstract.
Yes, that's it, precisely.
Okay, but that feels like the ultimate challenge. I mean, if you're trying to generate something that sounds natural and flowing, but you're not using pre-recorded samples,
right? What
stops it from just sounding like, chaotic, random noise?
Well, because simple randomness is chaotic. Human speech isn't random at all. It's predictable, but within a certain set of rules.
Okay.
So the challenge was translating those flowing, implicit, almost musical rules of Italian prosody.
Like where an accent should fall or how your pitch rises.
Exactly. Translating all of that into a computational system that is both predictable and variable.
So it needed structure, but also fluidity. It needed a sort of internal history of what it just did to inform what it does next.
Precisely. It needed a memory of its previous state.
The syllable it just used, the pitch.
Yes, the duration, the pitch interval it just selected, all of that to probabilistically decide the next one.
Which is why they landed on, what was it?
Hierarchical Markov chains. It was the perfect solution. They just divided the complexity into these cascading levels.
So a small decision is controlled by a bigger one.
Exactly. A micro-level decision, like syllable length, is immediately constrained by a higher level decision, like the total length of the phrase.
Okay, let's start small then. Let's look at the ground level, the microarchitecture of the sound itself.
Good idea. At the lowest level, everything is broken down into two foundational matrices. They define the immediate dynamics.
And first up, focusing on rhythm, is the syllable matrix.
Correct. The syllable matrix is a very minimal 3x3 structure. It just governs the immediate rhythm and accent, the timing.
Why 3 states? Why not 4 or 10?
Well, linguistically, for Italian prosody, these 3 states really cover the core needs. You have state 0, which is the short syllable.
Brief duration.
Right. Then state 1 is the long syllable, a bit more extended. And state 2 is the tonic accent, the emphasized syllable.
And that's all you need.
That's all you need to model the necessary timing and emphasis within a word or a little microphrase.
Okay, but in any probabilistic system, calibration is, it's everything. You can't have the machine getting stuck on a long syllable forever.
No, you can't.
So how did they validate the probabilities inside this 3x3 matrix?
They enforced a really strict calibration rule. For the system to be stable and, grammatically valid, each of the 3 rows in that matrix must have its probability weights sum up to exactly 1.0.
Okay, so let's unpack that. If the system is in, say, the short syllable state,
which is row 0.
Right, row 0. The chance of it then going to a long syllable or an accent or even another short syllable, all of those chances have to add up to 100%.
Exactly. That ensures that every single time a syllable state is determined, the machine must transition to one of the 3 possibilities. The distribution is always balanced. It's just simple matrix math applied to linguistics.
Okay, this is where it gets really interesting for me. Shifting from rhythm to the local melody with the word matrix.
The 5x5.
Yes, a bigger 5x5 matrix. And this doesn't decide what word comes next.
No, not at all.
It decides how the pitch moves from one syllable to the next, just locally.
It handles that immediate, localized melodic contour. The little jitters and movements that make speech sound lively and not, flat.
And the 5 states, they're really descriptive.
They are, and wondrously so in Italian. You have static, poco su,
little up,
poco giù, little down,
yeah,
and then tanto su, very up, and tantaju, very down.
I'm curious how something so simple, just 5 options, avoids sounding robotic. What's the output here? Is it just an abstract command, like go up?
No, and that is a key insight into the architecture. It's not an abstract state. The output is a direct, tangible command. It's a relative musical interval.
An actual musical note chain.
Pretty much. If the matrix picks a poco state, the system immediately translates that to a ±1 semitone change in pitch.
And a tanto state.
That translates to ±2 semitones.
Wow. So the system is incredibly direct. The machine is essentially singing the syllables using these calibrated probabilistic movements.
And that calibration brings us right back to validation. We know the 3x3 matrix needed its rows to sum to 1.0.
So the 5x5, it has a total validation sum of 5.0. You have to explain why, because I hear 5x5 and I'm thinking 25 cells, not a sum of 5.0.
Right. It's a fair question.
Yeah.
It's because the system is really executing 5 independent decisions inside that structure. So you have 5 independent rows. And for the system to transition validly from any of those 5 states, each of those 5 rows still has to sum to 1.0.
I see. So you have 5 complete probability distributions happening at once.
Exactly. So the sum of all 25 weights has to mathematically be 1 times 5, which gives you 5.0. It's the metric they used to make sure the whole local pitch system was calibrated.
To avoid any bias, like the pitch just constantly rising forever.
You got it. That distinction is so critical. It shows they weren't just guessing. They built the validation rules right from the logic of the system itself.
So with those microdynamics nailed down, the syllable length, the local pitch jitter, they had to move up to the macro structure.
To the breath, or what they call the phrase.
And I noticed they very wisely avoided the absolute nightmare of trying to control individual word lengths.
Oh, absolutely. That would have required actual linguistic synthesis, parsing grammar.
Dictionaries rule.
A completely different project. They avoided that. Instead, they focused on the rhythmic boundary of the utterance. They called it fraseggio a tempo determinato.
Determined time phrasing.
Right, and it's controlled by very simple triggers. You have phrase up for the start, the inspiration, and phrase down for the end, the expiration.
So what defines the length and the shape of that breath?
Length comes first. That's handled by the phrased matrix, which is just a simple 1x4 array.
And at the very start of the phrase, it makes a single choice.
A single probabilistic decision on the phrase's total length.
And the possible lengths are really specific. They're constrained to odd numbers of syllables, 3, 5, 7, or 9.
Yes.
Why so constrained, though? I mean, isn't forcing the phrase length to be an odd number and capped at 9 a little counterintuitive if you want something organic?
That's a great question.
Human sentences don't really stick to neat boundaries like that.
You're right, they don't. But the constraint is actually intentional. It's for stability and for a natural rhythm.
How so?
Well, phrases in natural Italian speech often do cluster around those kinds of lengths for balance. If they allowed just any length, the system would struggle to place the melodic contour correctly.
So it's a necessary simplification.
A necessary simplification to ensure rhythmic balance in a purely synthetic system. It models the short, contained utterances of casual conversation.
Okay, that makes sense. So once the length is chosen,
then the global structure is selected by the array phrasic. This is a 1x3 array, and it determines the overarching global melodic trend.
Will the whole phrase be ascending, descending, or ad arco?
Ad arco, yeah, like an arch or a parabola.
This brings us to what feels like the core structural challenge. You have these two conflicting forces. On one hand, the local jittery expressive pitch changes from the 5x5 word matrix.
Right.
And on the other, this smooth, broad, predetermined melodic arc from phrasec. If you just add them, you could ruin the global intent.
Exactly. It would be like drawing a smooth mountain range and then letting a toddler just scribble randomly all over it. The mountain range, the intent would be totally lost.
So what was the solution?
A linear modulator. In the system, they called it the Rampa.
A rampa, like a ramp, a steady incline or decline.
Correct. The Rampa generates a constant, smooth pitch offset. It's based on two things: the global contour that was chosen, and where you are in the phrase, which is tracked by the syllable counter.
So it doesn't fight the 5x5 matrix.
No. Critically, it doesn't fight it. It provides the foundational layer of pitch.
It provides the intention. So if the global contour is ascending, the rampa is constantly applying a slight upward bias, and that bias gets stronger as the phrase progresses.
Which leads us to their final pitch calculation formula. It's actually quite elegant.
It is pitch finale, pitch base, plus Rampa linearity contorno, plus the delta from the word matrix.
The change from the word matrix, yes.
That equation is so insightful because it separates structure from chaos.
It does.
The Rampa controls the oscillatura melodica, the melodic backbone.
And the local 5x5 matrix just provides the expressive gorgitio.
Which is, what, like a vocal wobble?
Deviations.
Exactly, vocal deviations or wobbles. Without that Rampa, the output would just be a series of localized pitch changes. It would sound like a random walk with no direction.
But the Rampa tells the listener, this is a statement, or this is a question.
By providing that controlled, intentional arc. The local wobble then gives it that human, imperfect quality so it doesn't sound like a boring, pure sine wave. So the Rampa provides the macro meaning, and the Markov chains provide the micro texture. What a fascinating division of labor.
Yeah, it is. But building a complex, flowing system like this, based on Markov chains, it introduces enormous testing difficulties.
Of course. If a system is designed for randomness, how do you even verify that it's working correctly?
That's a huge problem.
So let's talk about the tools they built in to ensure stability and control over all that probabilistic chaos.
Okay, so we start with termination. The phrase has to end cleanly when its chosen length is reached.
You can't have it just running on forever.
No. This is handled by a standard control circuit, a gate, which in pure data is the Spigot object.
And it's just tied directly to the syllable counter.
That's right. It ensures the system shuts off generation precisely when the length chosen by phrased is hit. It's a computational equivalent of not running out of breath mid-sentence.
And then every new phrase needs a totally fresh start. No baggage from the last phrase.
Absolutely. The complete reset function is fundamental. It clears all the counters, resets the probabilistic decision points back to 0 at the start of every single cycle.
But the most sophisticated element, and probably the most necessary for any complex generative system, has to be reproducibility.
Oh, for sure.
If a bug only happens one time out of 1,000 cycles, how do you possibly catch it?
This is where the engineering really shines. The seed function. It is an absolutely essential debugging tool.
What does it do?
It locks the internal random generators. So if a developer inputs the same seed value, the system will generate the exact same sequence of probabilistic transitions, rhythm changes, and pitch movements over and over again.
Wait, so the same seed guarantees the same random output? That sounds like a paradox.
It is the paradox of pseudorandom number generation. The numbers look random, but they're based on an initial calculation starting point.
And the seed locks that starting point.
It locks that starting point, so they can reliably recreate the exact moment the system fails, debug the precise weights that cause the error, and then verify the fix.
Even in a system designed for flowing unpredictability.
Yes. Without that seed function, developing a stable Markov chain architecture would be, well, nearly impossible.
It's the ability to pause and study the chaos that lets them master it.
So what we've really seen here is a highly structured, probabilistic machine that successfully models the breath, the rhythm, and the melody of human speech.
But not through recording.
Not through recording at all, but by meticulously calculating transitions between states. It's a pure computational model of expression.
And I think the final takeaway for me is how this architecture uses mathematical rigor to create the illusion of something organic and unpredictable. Every single decision, from that micro-level pitch wobble to the macro-level phrase length, is governed by these specific calibrated sums.
1.0 for the internal decision.
5.0 for the complete pitch matrix. That foundational discipline is what makes the generated speech feel structured, yet totally unique every single time.
And it forces you to ask some pretty deep questions about language itself.
Right.
If something is fundamentally human and spontaneous, as the melody and the timing of our voice can be broken down, quantified, and rebuilt.
Using just 3x3 and 5x5 matrices controlling these little steps and big ramps.
Then where does the true complexity of language really lie?
Is it in the rules they set up? Or is the deepest mystery still buried in that initial careful calibration of the probability weights?
Yeah.
The tiny difference between a 1.0 and a 0.9, the difference between sounding like a machine or sounding like a person breathing. That's something for you to mull over until our next deep dive.